All right, today's topic is electromagnetic induction. We kind of saw a little bit of this at the third part of the messing with magnets lab. This is the discovery that kind of ushered in the modern world with electrical appliances and electric motors and generators. This is a picture of Michael Faraday. Kind of one of the lesser known, kind of underrated scientists in history. He made some cataclysmic discoveries, this being one of them. He also discovered refrigeration, things that he discovered literally changed the world, but he had zero interest in getting credit for it. So largely he's gone unnoticed in history, other than a few things named after him, which is kind of nice. So, electromagnetic induction. It is kind of the hinge point between electricity and magnetism. They're very closely related. How closely related, I don't know that we fully have come to grips with that. I think the conversion back and forth between them will become more significant, and I'm not sure the word easier, but more practical and played out as our understanding of quantum mechanics and relativity get enhanced. So formally, it's the phenomenon that where we're inducing voltage, which is electric pressure in a conductor, meaning a wire, by changing the magnetic field around the conductor, or it should say relative to the conductor. So here somebody is just moving a magnet near a wire, and a current flows through the wire. Or you can move the wire relative to the magnet and a current flows through the wire. It doesn't matter. And all the wire does is trap the change in the electric field due to the change in the magnetic field. Okay, so you remember this demo in the third part of the messing with magnets lab. I had some coils. I moved a magnet in and out. When the magnet went in one direction, the current flowed in one direction. When the magnet went in the opposite direction, the current flowed in the opposite direction. This shows that same phenomenon. Now, Faraday's law. Faraday got credit. He probably is due that credit, but an American scientist, Joseph Henry, concurrently discovered the same thing, but we name it after Faraday. So he says that an induced voltage in a coil is proportional to the number of loops in the coil. So here there are 2, here there are 4, here there are 6, and so on. And the rate at which the magnetic field changes within those loops. Okay, so here's the equation, just to show you that it's directly proportional to n, the number of loops, and then delta, I forget the name of that Greek letter, that stands for the change in the magnetic fields, or formally the magnetic flux. And you can think of them as being interchangeable, although technically they're not. The flux is what is produced by the changing magnetic field. It's kind of like the difference between electrons and charge. So we say that current is the flow of charge, but it's not really technically the flow of electrons, even though the electrons produce the charge. And similarly, the change in magnetic field produces the magnetic flux. Okay, so here's a lady with a primitive motor, a number of coils, and a magnet that she's moving back and forth, and it's producing an electric current. Okay. Now, interestingly, as you'll see in one of the demos, moving a magnet through the air produces electric fields. And if there's a conductor nearby, especially if the conductor is in coils, then the magnet moves more. It's more difficult to move the magnet. So yeah, I'll demo this by taking a metal pipe and dropping the magnet through it, and the magnet does not fall at G. It falls slower because of the interaction with the conductor. Okay, so The two most important outcomes of this, at least currently, pardon the pun, are generators and motors. And as you saw in that last part of the Messing with Magnets lab, that motors and generators are basically the same thing. It's just a question of what's the input and what's the output. So what does a generator generate? Well, it generates electricity. From what? From mechanical energy. So you put in oomph, you put in work, you put in mechanical input, whether it's water flowing through a dam, pardon my language, or wind blowing and moving a wind turbine, or steam expanding and pushing a turbine, which pushes a generator. Okay. So mechanical energy in and electrical energy out. So what you have is a permanent magnet that is, actually it's the loops generally that move, but it doesn't matter. So the loops have to move relative to the magnet, or the magnet relative to the loops. And because the loops change in orientation in 360 degrees or 2 dimensions, the current that is produced is alternating. Okay, so this diagram shows that it would be very much the same thing as if you took a magnet and spun it, alternating north-south, north-south. In the same vein, the plane of the loop is changing, alternating between north and south. Which end of the loop is north and which end of the loop is pointing towards the south. Okay, now in terms of how the generator, the alternating current looks, we get this nice lovely sine wave. Okay, one direction and then the other. So this is kind of what a motor looks like, or a generator looks like. So you have the mechanical energy input, this in this case from, from steam. It could be a wind turbine, it could be any kind of mechanical device. And the generator turns, the loops are in here, and then the magnets are here. So what's the difference between a generator and a motor? What makes the motor work? Well, electrical energy is put in and mechanical energy is put out. Okay, so motors do work. And contrary to popular opinion, electric motors are just as powerful, if not more so, than big motors that go vroom vroom and make lots of noise and pollution. And they're at least twice, if not more, efficient, depending on the electric motor. All right. The next video lab that we will do, I'll have a bunch of demos on electromagnetic induction, and then a separate video lab will actually make an electric motor. Oh, it would be, I wish we could all be together to do this, because it's a super fun activity. All you get is a battery, a couple of paper clips, some alligator clips, and a magnet, and then a bunch of wire. It's called magnet wire or enameled wire, and you make a bunch of coils, and then you run current through it, and the current that runs through this armature produces a magnetic field that alternates, and it interacts with this permanent magnet, and the permanent magnet pushes on the magnetic field of the armature, and you get motion. And they spin amazingly fast, and it's pretty fun. So there you have electromagnetic induction. Oh wait, here's how a motor looks inside. Oh wait, shoot. Okay, so I got a lot more to cover. Yeah, I forgot to talk about transformers. Transformers are really amazing. They're almost like magic. So you have two parts to the transformer, and we're not talking about the science fiction movie. Um, so you have a primary set of coils and a secondary set of coils, and those coils are not connected to each other. It's the magnetic field in the primary coil that interacts with the magnetic field of the secondary coil, and you get a voltage change in um, the two sets of coils. Okay, so here's an example. So you have electricity going into the primary coil, okay, running through it, and you get this magnetic field induced in the primary coil. Then you put a conductor, just a big bar, metal bar in between that allows the current to flow in, and then this flowing current induces an electric field or electric current. Excuse me. This magnetic field induces a current in the secondary coil. And depending on the number of coils, because of Faraday's law, you can either step up or step down the amount of current, or voltage rather, and consequently the current flow. Okay, so what do we mean by step up or step down? So here you have the same number of coils on one side in the primary and secondary. So you're going to get the same amount of current. Here, it's a step. There's two coils, so it's a step up. You have 1 volt in, 2 volts out. Okay. Now, law of conservation of energy. You can't actually get an increase output and input. So it's the product. Power is the product of voltage and current. So the voltage times current on the primary side equals the voltage times the current on the secondary side. So if the voltage goes up, then the current goes down. All right, so the way power plants work, they produce 6,000 volts of electric pressure voltage. We step it up to transmit it over great distances. With a step up in voltage, there's a step down in resistance, equals IR. Okay, so with less resistance, then the wires don't heat up as much, and less loss of energy, just ambient energy radiating out. Okay, then it stepped back down to city power stations, and then it stepped down further for household use. And the city power station are like the ones that are on Lincoln and about F or so. Okay. Now, electromagnetic waves and electromagnetic induction. As I mentioned, electricity and magnetism are closely related. How closely related? Well, what is light? Light is an electromagnetic wave. There's actually two fields within every beam of light, and they interact with each other relativistically and give us the wonderful stuff that we know about. Those interactions, I think, are going to revolutionize energy production and energy usage when we get our head out of the sand and realize that fossil fuels are archaic ways of doing things. We need to move into the 21st century with not just our devices, but with our energy use and energy production.